Today we are going to look at the powers and roots of complex numbers, and this is where you will see the Moivre's theorem. So the Moivre's theorem, as you can see here, in mathematical expression, it is written such that a complex number z, when you take it to the power of n. So here, if you expand z in terms of the polar representation, you will see that this is r e I theta, and when you take the power of n, so this is you will get this expression r to the power of n and exponential term I n theta. So here, if you remember, e I theta is equals to cos theta plus minus sin I sin theta. So when you take the complex number to the power of n, here the Moivre's theorem states that you can just simply multiply the angle by n. So if you, on the other hand, if you take the n root of the complex numbers like this, so instead of a z to the power of n, now you're taking z to the power of 1 over n. And here this is the same as equation number 1 here, but instead of multiplying the theta by n, you're actually taking theta and you divide it by n, right? So this is the Moivre's theorem, and it is good to see how we apply this into solving some equations. So let's go to the first example over here. The first example here, they give you cos pi over 10 plus I sine pi over 10, and the whole thing you're going to take it to the power of 25. So this looks to be very complicated. 25 is a huge number, and if you do not have the Moivre's theorem, then things are going to get complicated. So if you apply the Moivre's theorem, you will see that you just have to simply take this is my n here, n equals to 25, and I just have to multiply my angle, in this case pi over 10 by 25, so that I have this expression now in equation number 3, where this is cos 25 pi over 10 plus I sine 25 pi over 10, and then you can simplify these numbers by dividing both the numerator and the denominator by 5, so that you have now cos 5 pi divided by 2, cos 5 pi over 2, and I sine 5 pi over 2. And here you will see that the cos 5 pi over 2 is going to be equals to 0, whereas sine 5 pi over 2 is equals to 1, and therefore this expression is equals to I. So now you can also solve this if you remember that cos pi over 10 plus I sine pi over 10 is equals to ei pi over 10. So ei pi over 10 to the power of 25 will give you here exponential I 25 over 10 pi. So now this is again you simplify this so that now you have ei 5 over 2 pi, and 5 over 2 pi here you can write it in terms of 4 plus 1 over 2 pi, and now 4 divided by 2 is just simply ei 2 pi over here, and you multiply it by ei pi over 2. So now you're going to evaluate this one term by one term, and ei 2 pi is going to give you 1, because if you remember, this is cos 2 pi plus I sine 2 pi. So sine 2 pi is going to be equals to 0, so you only have the real part, which is cos 2 pi, and this is equals to 1. On the other hand, exponential or ei pi over 2, you will get I, because your cos pi over 2 is going to be 0, and sine pi over 2 is equals to 1, so therefore you have I over here. So when you multiply, then you will get I. So here you see there's two ways to do it, that is based on either you use the cos and sine, or you just use it in terms of the polar form, which is in the ei theta, and they lead you to the same answer. So now let's go to example number 2. We'll just scroll down a little bit, and here we are in example number 2, and here they want you to find the cube roots of 8. That is, you want to take this expression. So here you will see that if you press this into the calculator, they will give you an answer which is equals to 2, right? But then when you consider the imaginary parts, then you will see that that there are two more answers to it. There are two more roots to this. So here what we want is we want to write the complex numbers in terms of the in polar form, and rei theta you're going to take to the power of 3, and this will give you equals to 8. So here you see that I have on the right hand side, this is a real number. So it means if I expand this term on the left hand side, I have r to the power of 3, and this should give me equals to 8. And the term which is related to ei theta, now when you multiply by 3, or you take a power of 3, so you will have e3 theta I equals to 1. So that now when you take this term r to the power of 3 multiplied by exponential 3 theta I, 8 multiplied by 1 will give you 8. So now you have to solve this term separately and this another term separately. So here the r to the power of 3 equals to 8. The answer is very easy because r is just simply equals to 2. So now we have to evaluate the angle part, which is the exponential 3 theta I. So here you remember exponential 3 theta I is written as cos 3 theta plus I sine 3 theta. And so here this is going to be equals to 1 because my right hand side this whole thing must be equals to 1, and therefore the imaginary part is not existing over here, and this means that my cos 3 theta is equals to 1, and I sine 3 theta, the sine 3 theta here is equals to 0. Therefore here when you take the cos 3 theta equals to 1, you just have to rearrange it so that my angle theta now is going to be equals to arc cos of 1 over 3, and this is equals to 0, 2 pi over 3, 4 pi over 3, and etc. So now here it means my cube of the cube roots of this number 8 is then 2, which is stands for this 2 alone, because 2 cos my theta is equals to 0, so ei theta or ei0 is going to be 1, and therefore 2 is a root. And then you have 2 exponential I 2 pi over 3 and 2 exponential I 4 pi over 3, right? So these are the 3 roots. And here let me just go down a little bit. So this is a plot where I plot the cube roots of 8. So there are three values here. So 2, 0. So if I plot it in terms of the in the polar form, so I have r equals to 2, theta equals to 0, and this lies at this point. And the other point, which is 2, r equals to 2, and angle equals to 2 pi over 3, that is at this point. And r equals to 2, angle equals to 4 pi over 3, it is this point. So here you see this is actually a circle which where the radius is equals to 2. So now let's go to the third example where you want to find the fourth root of negative 64. So this is slightly different than the previous example, where in the previous example you are taking the root of a positive number, but in this case this is a negative number, so this is negative 64. So the first thing that we need to do is to remember that we will write the complex number in a polar form. So you have re exponential I theta, and this whole thing, when you take it to the power of 4, this is going to give you negative 64, right? So then here you will try to rearrange it a little bit so that the negative 64 can be written in terms of 64 multiplied by negative 1. And negative 1, we should remember that negative 1 equals to I squared. So this is negative 64 is the same as me writing 64 I squared, okay, or 64 multiplied by negative 1. So now let's look at the left hand side. Here you have a radius r to the power of 4, and this should give me 64. So there is, on the right hand side, there's another number which is -1, and this means that my left hand side, the exponential term, that is exponential I for theta, is going to be equals to -1. Now we will solve for the radius first. So the radius r to the power of 4 equals to 64. When you take the fourth root, you will see that this r is equals to 2 square root of 2. So this is the radius of this circle on the complex plane. Whereas the imaginary part, now I have this exponential I for theta equals to -1. And if you remember, this e I for theta is equals to cos 4 theta plus I sine 4 theta. So there is no I over here on the right hand side, so it means my cos 4 theta should be equals to -1. So then I just have to rearrange a little bit so that I have 4 theta over here, and this is equals to cos arc cos of -1. So the arc cos of -1 will give me pi, 3 pi, 5 pi, 7 pi, and so on. But we are only concerned with this 4 because if you go further than this, then you are going to get the answer at the same quadrant. So now the theta is just simply taking this pi, 3 pi, 5 pi, 7 pi, and you divide them by 4 because you have a 4 on the left hand side here. So finally the answer that I want is theta equals to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And this means the roots of the fourth root of -64 is simply this answer. So you have to multiply the radius, that is 2 square root of 2, by the angle which is given in this expression. So now is it possible to plot this on a complex plane? So I will just leave this to you for you to do as an exercise, and you will see that they lies on the 4 different quadrants. So now I leave the following exercise for you to try to do. Please find the roots of these following numbers. There are 5 of them, and the second question here is you want to prove that the sum of the 3 cube roots of 8 will give you 0. So we will do this, and we will discuss this in our following class.